What if the universe isn't as silent as it seems? Imagine ripples, echoing through the very fabric of space-time, carrying secrets from before stars even ignited. These are gravitational waves, and they're whispering tales from the universe's fiery birth, waiting to be deciphered. Feel that. No, not the floor beneath your feet, but the subtle undulations of reality itself. Deep in the cosmos, unseen forces are creating cosmic tremors, distortions in space-time that travel across billions of light-years. Prepare to journey to the dawn of everything, as we explore these powerful ripples. Think you know the universe? Think again. What if the most profound secrets about our origins aren't hidden in light, but in vibrations? Gravitational waves are the universe's primal scream, a direct link to the moments after the Big Bang. Unlock the hidden symphony of the cosmos and discover what these ancient echoes reveal. Imagine a universe not silent, but humming with the echoes of colossal events, a symphony of gravity. In this quiet hum, there are no instruments carved by human hands, no strings, no brass, no drums. Instead, the notes arise from stars collapsing, black holes colliding, and space-time itself trembling as if stirred by unseen winds. This hum is older than language, older than the breath of planets, and it travels effortlessly through the cosmic dark, crossing billions of light-years without ever slowing. To imagine this universe is to imagine existence itself as a living ocean, where each ripple tells a story too vast, too ancient, and too powerful to be contained in words. Every fluctuation, every trembling line, is a memory etched into the very architecture of space-time, waiting patiently for a mind to notice it. In such a universe, silence is an illusion born from our limited senses, because our ears were never designed to hear the bending of reality. Yet the waves are there, stretching and squeezing everything they pass through, like the soft pulse of something immense breathing in the dark. If you were to drift in the void without a ship, without a suit, stripped to pure awareness, you would not hear these waves, but you might feel them, subtle as the passing of a dream, nudging the fabric of your own existence. They are the background whispers of creation, a constant reminder that the cosmos is never still, never finished, always reshaping itself in ways too gentle or too violent to ignore. These gravitational murmurs are born from events so extreme that even light struggles to escape their influence. Picture two black holes spiraling toward one another, devouring the distance between them, moving faster and faster as if pulled by an invisible hunger. Their final collision sends out a blast not of fire, not of sound, but of warped space-time, stretching the universe like a drumhead struck by a cosmic hammer. This is not simply energy released, it is the universe announcing that something profound has happened, something capable of rewriting the geometry of reality for an instant before fading into the endless dark. But these waves do not fade entirely. They travel outward forever, weakening but never disappearing, like the faintest vibration lingering in a pool long after a stone has sunk to its depths. For billions of years, they wander through nebulae, star fields, clusters, voids, collecting stories of everything they pass. They weave through galaxies the way a breeze moves through tall grass, unnoticed by the stars yet subtly shifting the shape of everything they encounter. And after crossing unfathomable cosmic distances, a few of these ancient waves finally arrive at one pale blue world orbiting a modest star in an ordinary spiral galaxy. On that world, humanity built instruments delicate enough to notice these passing waves, observatories capable of detecting distortions thousands of times smaller than a single atom. In giant tunnels cooled and quieted to near perfection, lasers reflect between mirrors that must remain perfectly still. Yet when a wave sweeps through, the mirrors shift ever so slightly, dancing to a rhythm older than Earth itself. The detectors respond with the softest whisper of data, a pattern of stretching and squeezing that corresponds to a moment when two massive objects collided somewhere deep in the cosmos. To appreciate this is to appreciate the astounding patience of the universe. It produces phenomena on scales we cannot fully comprehend, then allows them to journey untouched for eons before finally brushing past our fragile instruments. And when they do, it is as though a story that has been waiting for billions of years finally finds someone capable of listening. These waves are not loud, they do not demand attention. They are gentle messengers, carrying tales of destruction and creation without ever lifting a finger of flame. Imagine, too, how many waves have passed by unnoticed before we even learned what they were. For most of human history, the universe's gravitational music played freely in the dark, while our ancestors gazed at the stars with wonder but without the tools to decode the underlying rhythm. Only recently have we learned to translate those vibrations into meaning. It is like discovering that a painting you've admired your whole life also contains a hidden layer visible only under special light, revealing a new world entirely. Each wave that reaches us now can be traced back to a specific cosmic event, a unique signature like a fingerprint. A wave from colliding neutron stars has a different melody than a wave from merging black holes. One is sharp and intricate, like the plucking of a cosmic harp. The other is deep and powerful, like the resonant hum of a massive drum. And as we collect more of these signatures, the universe begins to reveal the complexity of its ancient orchestra. But the symphony is not continuous, it is punctuated by silence intervals where nothing detectable reaches us. In those moments, the universe feels quiet, though it never truly is. We wait, knowing that somewhere in the depths, another collision is brewing, another violent act of creation ready to send its waves racing across the cosmos. These waiting periods remind us that even the grandest cosmic dramas unfold slowly, in timeframes far beyond human lifespan or imagination. When a new wave is detected, scientists celebrate not because it is loud or dramatic, but because it is a glimpse behind the curtain of existence. Each detection offers clues about the behavior of matter under extreme pressure, about the nature of black holes, about the fabric of spacetime itself. Every wave is both an answer and a question, an invitation to explore the deepest mysteries of the universe with renewed curiosity. This humbling perspective shifts how we see ourselves. We are not separate from these waves, we are woven into the same fabric they traverse. When spacetime ripples, Earth ripples with it, and so do we, our atoms, our bones, our thoughts, all subtly stretched and compressed by events that occurred millions or billions of years ago. We are, in a literal sense, participants in the universe's ongoing symphony, even if we rarely feel the strings that bind us to distant stars. Imagine sitting quietly in the night, the world hushed around you, and remembering that at that very moment gravitational waves may be passing through your body. They slip through effortlessly, leaving no pain, no disruption, only the faintest echo of something unimaginably far away. In that moment of awareness, the universe becomes less of a cold, distant expanse and more of an intimate presence, gentle, immense, and always in motion. The beauty of these waves lies in their honesty. They do not hide what happened, they carry the raw imprint of cosmic events exactly as they occurred. If two black holes collided in perfect symmetry, the wave is smooth and balanced. If they merged unevenly, the wave wobbles or twists. The universe leaves fingerprints, and gravitational waves are among the clearest and most unfiltered records of its actions. Yet the waves alone are not enough, humans must interpret them. It takes extraordinary precision, patience, and imagination to transform faint distortions into meaningful insights. Scientists must tune out the noise of Earth, trucks rumbling, storms gathering, vibrations from tiny geological shifts to isolate the pure signal. It is like trying to hear a single raindrop splash on a mountaintop while standing in a bustling city. But with enough care, the raindrop becomes audible. When the first gravitational wave was detected, the world felt a shift, not in spacetime but in understanding. For the first time, humanity had more than eyes to perceive the cosmos, we had ears. And what we heard confirmed Einstein's predictions, validated decades of effort, and opened an entirely new way of observing the universe. It was as though a door we never knew existed suddenly appeared, revealing a breathtaking landscape hidden behind the stars. The universe, once studied primarily through light, radio, infrared, optical, X-ray, now offered a second language. Light tells us what surfaces look like, what elements burn inside stars, how galaxies shine. But gravitational waves tell us what the universe does when structures collapse, when mass accelerates violently, when space-time itself contorts. One is the language of illumination, the other is the language of motion. Through these waves, we discovered things we couldn't have known otherwise: black holes that were heavier than expected, mergers that occurred in regions long thought improbable, collisions so distant that even their light may never reach us. The waves revealed truths that had been hidden behind cosmic curtains, unreachable to even the most powerful telescopes. And yet, with every discovery, new mysteries appear. How many types of black hole mergers exist? Are some waves produced by phenomena we haven't even imagined yet? Could the universe contain exotic objects, boson stars, primordial black holes, or other entities that generate patterns unlike anything we've seen? The symphony is vast, its composition unfinished, its notes still arriving in unpredictable intervals. Patience becomes a form of devotion in this science. Scientists wait years for the right signal, monitoring the detectors constantly, ready to sift through the data when the faintest tremor appears. The universe does not rush, and so neither can we. The waves come when they come, each one a gift of unimaginable age and distance. And while we wait, we dream not just of what we might detect next, but of what these waves say about our place in the cosmos. They remind us that we are small, yes, but also connected. The same laws that govern the dance of black holes govern our own atoms. The same space-time that ripples across galaxies flows through every cell in our bodies. These waves also remind us of impermanence. Stars die, galaxies collide, space-time bends and settles. Everything is in motion, everything transforms. But in that transformation, beauty emerges, patterns, rhythms, and stories written not in ink but in gravity. Think of how extraordinary it is that we, fragile beings of carbon and water, living on a tiny planet, have learned to listen to these cosmic murmurs. The universe has been singing since its earliest moments, but only now have we developed the sensitivity to hear it. It feels almost poetic, as if the cosmos waited patiently for conscious life to evolve instruments precise enough to perceive its quiet truth. So imagine again that universe humming, and imagine yourself within it, not as an observer on the outside, but as part of the symphony. Because you are. Every atom in your body participates in the gravitational rhythm. You are not separate from the waves, you are shaped by the same forces that generate them. And as you breathe, move, and think, you add your own subtle presence to the ever-changing tapestry of space-time. And perhaps, one day far in the future, beings on distant worlds will listen to waves passing through them and hear echoes of events we cannot yet imagine, new collisions, new births, new transformations. The universe will continue to hum, and the symphony will continue to evolve, long after every star we know has faded. Until then, each wave that arrives is a reminder: the universe is alive with motion, filled with stories, and patient enough to let us discover them one gentle vibration at a time. How Einstein's century-old prediction of space-time ripples is now a palpable reality. It feels almost unreal that an idea once scribbled on paper, born from pure thought, has become something we can detect, measure, and interpret with astonishing clarity. When Einstein proposed that massive accelerating objects would send ripples through space-time, it was a leap of imagination so profound that even he doubted humanity would ever have the means to observe such faint tremors. Yet here we stand, in an era where the universe's deepest convulsions leave measurable fingerprints on instruments built with extreme delicacy. The wonder of it is not simply that Einstein was right, but that we have grown capable of verifying ideas that once lived only in the quiet space between equations and dreams. To appreciate how extraordinary this transformation is, imagine the early decades of the 20th century, when physics was being rewritten from the ground up. Relativity was new, controversial, and strange, challenging the comfortable view of space and time as rigid and inert. Einstein dared to claim that space could stretch, twist, and ripple like a living substance, a fabric woven so finely that it responded to the movement of planets and the birth and death of stars. For many, the idea seemed poetic rather than literal, too imaginative to be true, or too subtle to ever be confirmed. Even Einstein wavered at times, wondering whether gravitational waves would forever remain a mathematical curiosity. Yet the mathematics held firm. It suggested that when colossal masses dance, spiraling, merging, collapsing, they would send out waves that travel at the speed of light, altering distances as they passed. These ripples were thought to be so minuscule by the time they reached Earth that even the most advanced instruments of Einstein's day wouldn't stand a chance of noticing them. The scale of the distortion was absurdly tiny, so tiny that detecting it seemed equivalent to measuring a change in the distance between Earth and the Sun smaller than the width of a human hair. How could such a feat ever be accomplished by a species that still struggled with the basics of quantum mechanics? But human curiosity is persistent, and over the decades it turned skepticism into determination. Visionaries like Joseph Weber took the first steps, building massive aluminum cylinders in hopes of catching cosmic vibrations. Though his results didn't stand the test of time, his efforts lit a spark that inspired others. The dream didn't die, it evolved. It transformed into a long-term pursuit that demanded technologies not yet invented, patience not yet practiced, and international cooperation on a scale rarely seen in science. Slowly, methodically, humanity inched toward the edge of a new sensory ability. The development of interferometry was a turning point, a technique that uses the interference of light to detect incredibly tiny changes in distance. By splitting a laser beam, bouncing the halves back and forth along perpendicular tunnels, and recombining them, scientists realized they could detect shifts far smaller than a proton. The idea was bold, almost reckless in its ambition, requiring engineering precision so extreme it bordered on the impossible. But impossibility has never been a final barrier for the human mind. It is merely an invitation to keep thinking, refining, experimenting. As LIGO and later Virgo rose from the ground, they represented not just scientific instruments but vast leaps of faith. They required isolation from earthquakes, storms, and even the tiny vibrations caused by passing trucks. They demanded innovations in mirror coatings, vacuum technology, and lasers steady enough to resist the trembling of the Earth itself. The detectors became sanctuaries of stillness, vast corridors where light traveled in silence, waiting for the faintest whisper from the universe. And then, finally, after decades of dreaming and building and failing and rebuilding, the whisper arrived. In September 2015, space-time itself shuddered as two black holes collided more than 1 billion light-years away, sending out waves that gently brushed past Earth. The distortion it caused was unimaginably small, far smaller than an atom, but the instruments were ready. They had been listening for years, holding their breath. When the wave passed, the change it caused in LIGO's mirrors registered as a tiny pattern of stretching and squeezing, the exact signature described by Einstein's predictions. It was a moment that felt like the universe clearing its throat after billions of years of silence. Humanity had heard a new kind of sound, not through ears but through measurement, interpretation, and sheer intellectual audacity. The detection did more than confirm Einstein's theory. It announced that we were finally ready to explore a realm of cosmic events that had been invisible to us since the birth of time. It was as though a curtain had been lifted, revealing a hidden dimension of the cosmos we had never before been able to touch. The announcement sent ripples through the scientific community, waves of its own kind, emotional and intellectual. A century-old prediction had come alive, not as an abstract concept but as a measurable, undeniable reality. It was proof that the universe could communicate in more than light, more than particles, more than temperature and radiation. It could speak through gravity itself, through the shifting of space-time, through vibrations that carry the echoes of ancient catastrophes. Since that first detection, we've heard many more waves, each with its own story to tell. Some come from black holes spinning and colliding in the dark. Others emerge from neutron stars spiraling together until they erupt in a burst of light and heavy elements. Each detection deepens the validation of Einstein's vision, not because we doubt the theory, but because its predictions are revealed with such elegant consistency. Every new signal is a nod from the universe, acknowledging the truth of an idea formed long before we had the ability to test it. But perhaps the most astonishing part of this journey is not the confirmation of relativity, but the new frontier it opens. Gravitational wave astronomy allows us to observe the universe not as it appears, but as it behaves. It reveals the invisible, black holes with no light to betray their presence, collisions hidden behind dust and gas, events too distant to illuminate their surroundings. It allows us to study gravity not as a force alone, but as a dynamic, evolving structure that transmits information across unimaginable distances. Einstein might have been amazed, amused, perhaps even a little humbled to see how thoroughly his prediction has become reality. Because for all his genius, he doubted that the waves could ever be detected. It wasn't that he lacked faith in his equations, he simply thought the distortions would be too small for human hands and minds to isolate. Yet humanity has a habit of reaching beyond its grasp, pushing into territories even their discoverers could barely imagine. Einstein gave us the map, we built the instruments. What makes this transformation even more beautiful is the slow, deliberate patience behind it. The universe did not announce these waves loudly. It whispered them, gently stretching the distances between mirrors by a fraction of a fraction of a fraction of a particle's width. And humans, instead of expecting loud answers, learned to listen with extraordinary sensitivity. We grew quiet enough to perceive the faintest tremors of creation. Now, gravitational waves are not theoretical, they are data. They are patterns etched into computer screens, waiting to be decoded. They are signals that tell us about mass, spin, distance, and the cataclysmic ballet of collapsing stars. They have become as real as the light from galaxies and the dust from ancient supernovae. Einstein's ripples have become part of the toolkit with which we understand the cosmos. And with each new detection, our confidence grows not just in relativity but in our ability to perceive the universe with ever-increasing nuance. We are learning to read space-time like a language, slowly deciphering its grammar, its rhythm, its cadence. The waves show us that gravity is not silent, not static, not passive. It is expressive, reactive, dynamic, capable of carrying stories across the cosmic ocean. Einstein's century-old prediction is no longer a speculation tucked into the margins of physics. It has become a form of observation, a way of seeing through darkness, a method of touching events that occurred before Earth even formed. It has become a bridge between theory and reality, between imagination and measurement, between the whispers of space-time and the minds that learned to hear them. And yet, as profound as this achievement is, it feels like only the beginning. New detectors, more sensitive and more ambitious, are already being planned, machines that will listen to lower frequencies, further distances, older events. They will hear waves from the first black holes formed after the Big Bang, waves from cosmic strings if they exist, waves from phenomena we haven't yet conceived. The century-old prediction will continue to expand, evolving into discoveries Einstein never dreamed of. The ripples he described have become windows, and through them we glimpse the universe not as it appears to our limited senses but as it truly is, restless, interconnected, vibrating with the echoes of unimaginable forces. And standing here now, recognizing that these waves are no longer imaginary but real, measurable, and interpretable, we witness a story that bridges time itself, Einstein at his desk a century ago, and us today, listening to the universe breathe. The mind-bending concept of space itself stretching and compressing, even affecting you right now. It sounds impossible at first, like something pulled from the realm of fantasy rather than physics, yet it is one of the most profound truths of our universe. Space is not an empty container holding planets and galaxies, it is an active, flexible fabric that shifts and bends as massive objects move through it. This stretching and compression is so subtle on human scales that we never notice it, yet it continuously flows through our bodies, our homes, and our world, connecting us physically to distant cosmic events. You are immersed in space-time, woven into it, carried by it, and reshaped by it in tiny, tiny ways with every passing moment. When gravitational waves sweep through Earth, the space between your atoms expands and contracts, though the amount is so small you would never feel it directly. It's like being inside a vast, calm ocean while ripples pass beneath your feet, gentle, persistent, everywhere. The universe is not static, not rigid. It breathes with these tiny variations, these pulses of curvature, shifting distances in ways that defy ordinary intuition. And though your senses insist that nothing is happening, your very existence floats atop a fluid medium that never stops trembling with the aftershocks of ancient cosmic collisions. One of the most astonishing parts of this concept is how deeply it challenges our everyday assumptions. We grow up believing that space is fixed, that 1 meter is always 1 meter, that distances are unchanging. Yet physics tells us otherwise. Even without gravitational waves, space-time is constantly influenced by mass, motion, and energy. Earth curves the space around it. The sun bends the trajectories of planets. Galaxies twist space-time on colossal scales. And when gravitational waves arrive, they briefly modify the structure of that same space, like a passing tide gently lifting and lowering an anchored boat. To grasp this idea, imagine drawing a grid on a flexible sheet of rubber. If you press on one side, the grid lines stretch and compress. If you drag something heavy across it, the grid warps in waves. That grid is space itself, not just a background but a dynamic participant. And you are standing on that rubber sheet, living your life while the universe pushes, pulls, and ripples beneath your feet. Every moment is connected to the broader motion of the cosmos, even if you cannot perceive the shifting with your senses. The stretching of space is not limited to fleeting gravitational waves, it is fundamental to the structure of the cosmos. The universe as a whole has been expanding since the Big Bang, meaning galaxies are not flying through static space but are instead carried apart as the space between them grows. This expansion is another example of space acting like a fabric, not a void. On cosmic scales, this stretching defines the fate of galaxies and the evolution of clusters, controlling the architecture of existence itself. But gravitational waves add a new dimension to this picture. Unlike the slow, steady expansion of the universe, these waves are dynamic distortions caused by violent events, black hole collisions, neutron star mergers, catastrophic collapses of massive stars. When these events occur, space-time reacts, creating ripples that carry the imprint of the event outward in all directions. Those ripples don't stop at the edges of galaxies, they travel for billions of years, eventually reaching planets, moons, and even tiny creatures like us who have only recently learned how to detect them. Every gravitational wave that passes through you shifts the distances between your cells by an amount smaller than a proton. It stretches you vertically while compressing you horizontally, then reverses a moment later. These motions are not dangerous or disruptive, they are incredibly gentle, but they are real, manifestations of the universe's constant dynamism. You live in a sea of invisible motion, with space-time perpetually adjusting its shape around you. Consider how extraordinary it is that space-time can change shape at all. In everyday life, We think of space as a stage, a neutral setting in which things happen. But relativity shows us that the stage can tilt, ripple, and flex under the influence of matter and energy. Space is not passive, it is sensitive. It responds to mass like a musical instrument responds to touch. And gravitational waves are the notes played across that instrument, faint and subtle but fundamentally beautiful in their implications. This fluidity of space also means that distances are not absolute. Two objects may be separated by 1 meter in one moment and slightly more or less a moment later, depending on the ripples flowing through space-time. Even clocks, devices we rely on as the definition of consistency, tick at different rates depending on how space is curved or stretched around them. Your own perception of time is shaped by the same forces that shape distance. When you walk across a room, you rarely consider that the space you move through is not rigid. But if a massive event occurred billions of light years away and the gravitational waves from that event reached Earth at that exact moment, the space you step through would be subtly stretching and compressing as you move. You would never feel it, yet your motion would trace a path through gently shifting geometry. Everything you do, from blinking to breathing to thinking, happens inside a living mesh of space-time that is constantly shifting beneath you. This concept becomes even more mind-bending when you realize that the objects around you, your chair, your walls, your city, are all expanding and contracting simultaneously during a wave's passage. Yet because everything stretches together, the motion is nearly impossible to perceive. It's like being inside a giant balloon that expands and contracts evenly without any part of it pulling or tearing away from the rest. You float within the changes, carried with them, unaware of the tiny dance your body performs. The very idea that something can stretch everything and yet leave no sensation behind pushes against our intuitive understanding of the world. We are designed to feel pressure, heat, light, sound, but not the shifting of space-time itself. That sense lies beyond biology, beyond evolution, belonging instead to the realm of pure physics. Only instruments crafted with exquisite precision can act as our space-time ears, revealing the silent symphony we inhabit. Think about how gentle yet universal these waves are. A collision of black holes so powerful that it momentarily releases more energy than all the stars in the universe combined still reaches Earth in an almost ghost-like form. After traveling for billions of years, all that remains is a faint trembling of space-time, like the softest sigh drifting across a vast ocean. But that sigh touches everything, from mountain ranges to grains of dust to your own heartbeat, altering distances everywhere by the same fractional amount. This means the waves connect the cosmos in a very literal way. The stretching that touches your body may also touch a distant satellite, a cloud over the Pacific, and a piece of ancient stone buried deep under Earth's crust all at the same moment. The entire planet participates in the wave's passage, responding in unified, coordinated motion. It is a rare example of the cosmos affecting everything equally, without distinction or preference. The subtlety of this interaction highlights how small we are compared to the forces that sculpt the universe. Yet it also emphasizes something profound: we are not separate from cosmic events. The universe is not out there while we stand safely apart. Instead, those events, their consequences, their vibrations, and their echoes flow through us physically. Everything is connected through the shifting, bending fabric of space-time. What makes this even more astonishing is the philosophical depth behind it. We tend to view ourselves as locally bound beings, shaped by Earth, by biology, by human concerns. But gravitational waves remind us that we are also shaped, however subtly, by distant stars, by ancient collisions, by the universe's largest and most dramatic transformations. We exist within a cosmic context that touches our bodies whether we realize it or not. This kind of perspective brings with it a quiet sense of humility. Life feels grounded and ordinary, yet it occurs within a structure that transcends our senses by unimaginable margins. The floor beneath you is momentarily closer or farther from your ceiling because two black holes spiraled into each other long before Earth had life. Such a realization blurs the boundary between the intimate and the infinite. And perhaps this is the deepest beauty of the concept. It shows that the universe is not static but alive with motion, not silent but humming with unseen vibrations. Space is not a cold emptiness but an active participant in reality, a medium shaped by the forces that govern stars and galaxies. You are always inside its motion, always carried by its shifting form, always part of the cosmic dance whether you feel it or not. To live with this knowledge is to see the world differently, not less familiar, but more profound. Every moment unfolds inside a gently trembling universe, every breath synchronized with distortions older than Earth, every heartbeat beating inside a fabric that bends and flexes with the memory of unimaginable events. And though the motion is tiny, its meaning is vast. Space is not still. It never has been. And you, right now, are moving with it. The ingenious technology behind observatories like LIGO and Virgo, arms longer than cities, sensitive to a fraction of an atom's width. It almost sounds like the opening line of a science fiction epic, something you'd expect to belong to a civilization far more advanced than ours. Yet these instruments exist here, on Earth, built by human hands and sharpened by human patience. At their core lies a breathtaking ambition, to measure distortions. In space-time so tiny that they pass unnoticed by every living creature, every machine, everything except these monumental observatories engineered with almost unfathomable precision. Their long vacuum-sealed arms sprawl across landscapes like silent, linear monuments to curiosity, waiting for the universe to whisper. Each detector is essentially a colossal ruler, but one so refined that it can sense the smallest imaginable shift. The arms of LIGO, 4 kilometers each, form a giant L shape where light is sent racing back and forth. Virgo extends this geometry even further with 3-kilometer arms that operate as part of a global network. To build something capable of detecting movements on the scale of a 10,000th of a proton, something so small it defies visualization, is to push the boundary between imagination and engineering. That such an instrument works at all is a testament to decades of innovation, setbacks, and relentless pursuit of the nearly impossible. Light becomes the primary tool for these observatories because no physical object could ever be refined enough to measure changes this small. Even the most sophisticated mechanical device would buckle under thermal noise, quantum effects, or vibrations from the environment. But light, steady, pure, unburdened by mass, can serve as the ultimate probe. By splitting a laser beam and sending the halves down perpendicular arms, the observatories can compare how long it takes for each beam to return. If space-time stretches one arm and compresses the other, even by a minuscule amount, the returning beams will no longer match perfectly. This tiny mismatch becomes the signal. But the challenge is staggering. Earth is noisy, not just in the human sense, but physically, vibrationally, globally noisy. Air currents shake buildings. Ocean waves ripple through the ground. Trucks drive miles away. Raindrops add microscopic quakes. Even molecules in the ground jitter due to thermal energy. To detect a gravitational wave, the motion of the mirrors at the ends of the arms must be quieter than all of this, so quiet they barely move at all except in response to spacetime itself. To achieve this, the mirrors are suspended like pendulums, hanging from advanced multistage systems that isolate them from Earth's chaos. Each mirror is crafted with extreme precision, polished so perfectly that its imperfections are smaller than the wavelength of the light that strikes it. These mirrors become the silent gateways through which the laser beams bounce, thousands of times, amplifying the instrument's sensitivity. They hang in immense vacuum chambers cleared of nearly every molecule, because even a stray atom drifting across the beam could muddy the measurement. The observatories operate as sanctuaries of stillness, where the bustle of the world is held at bay to let the universe whisper through. Vacuum itself becomes a critical character in this story. The arms of LIGO and Virgo house some of the largest vacuum systems ever created, stretching kilometers with pressure lower than what you'd find in outer space. Maintaining this vacuum is an engineering feat equivalent to keeping an entire city block perfectly sealed, clean, quiet, and unmoving. Without it, heat from air molecules would distort the laser beams, scattering them and drowning out the faint signals astrophysicists hope to capture. Even the laser system is an achievement of extraordinary refinement. The beam must be incredibly stable, no flicker, no drift, no tiny vibration allowed. The power of the laser must be controlled with delicate precision, ensuring it remains bright enough to detect tiny shifts but not so powerful that it introduces extra noise. Every component of the system, from the detectors to the optics to the electronics, must be shielded from fluctuations in temperature, electromagnetic fields, and even quantum uncertainty. Quantum noise, in fact, becomes a limiting factor at these scales. Because light comes in discrete packets, photons, their arrival is not perfectly even, and this randomness introduces uncertainty. To overcome this, scientists developed techniques to squeeze light, reducing uncertainty in one property of the photons at the expense of another. This quantum trickery pushes sensitivity beyond what classical physics would allow, letting gravitational wave detectors peer further into the universe with each upgrade. Beyond quantum effects, thermal noise also poses a formidable challenge. Even at room temperature, atoms in the mirrors and suspension fibers jiggle, and this jitter creates subtle tremors. To combat this, advanced materials and cooling techniques are employed, using ultra-pure silica fibers and low-temperature systems that minimize thermal agitation. These strategies turn the mirrors into islands of serenity, where their subtle dance with gravitational waves is not interrupted by the restless energy within their own atoms. The observatories must also account for seismic noise, the tremors caused by Earth itself. These vibrations can come from natural sources like tectonic shifts or distant ocean waves, or from human activity such as construction, nearby traffic, or even footsteps. Sophisticated seismic isolation platforms lift the mirrors to a state of near levitation, using active feedback systems that sense the tiniest ground motion and counteract it in real time. The detectors become suspended worlds of near silence. All of this engineering culminates in an instrument so sensitive that it can detect changes in distance thousands of times smaller than a hydrogen nucleus. The sheer absurdity of this sensitivity is what makes these observatories almost mythic in nature. Yet they are real, built by thousands of scientists and engineers across decades. Their success is not just a triumph of physics but of human collaboration and persistence. When a gravitational wave passes, the detectors do not visually move. No vibration is felt. But in the data, buried in the steady hum of the instruments, a subtle pattern emerges, a faint variation that matches the predicted stretching and compressing of space-time. Sophisticated algorithms sift through mountains of noise to pick out these patterns, distinguishing cosmic signals from mundane disturbances. It is like listening for a single violin note in the roar of a storm. What's astonishing is that each detection requires not just one observatory but multiple. LIGO has 2 detectors thousands of kilometers apart, and Virgo in Europe acts as a third. When all 3 detect the same pattern at nearly the same time, scientists can triangulate the wave's origin in the sky. This network transforms gravitational wave astronomy from mere detection into localization, letting us map the universe in a completely new way. The coordination between these observatories mirrors the coordination within each one. Every subsystem must operate in harmony: lasers, mirrors, vacuum systems, feedback controls, cooling systems, optics, and data processing tools. If even one part falters, the entire instrument's sensitivity could collapse. Thus, maintenance becomes an art form, constant, careful, a balancing act between preventing interference and enhancing performance. Even the physical shape of the observatories plays a role. The long, straight arms must be perfectly aligned, extending over terrain that naturally curves with Earth's surface. The buildings must be designed to shield sensitive components from wind, rain, temperature changes, and wildlife. Some facilities even monitor nearby trees, because swaying branches can influence ground vibrations. Every detail matters. As technology advances, upgrades transform these detectors into even more powerful tools. New materials reduce noise, more refined lasers improve stability, and deeper vacuum systems enhance sensitivity. The observatories evolve with time, growing sharper, quieter, more attuned to the faintest tremors of the cosmos. Each new improvement opens the door to detecting weaker signals, farther events, and more exotic cosmic phenomena. What makes this network of observatories truly astonishing is how it redefines our sense of scale. Humans built structures kilometers long that can sense distortions trillions of times smaller than anything we can intuitively grasp. They operate at the intersection of the enormous and the infinitesimal, the cosmic and the atomic. Their size grounds them in the physical world, but their sensitivity reaches into realms that feel almost metaphysical. And yet, despite their monumental complexity, what they seek is simple in essence: a change in distance, a shifting of space-time, a ripple from a distant catastrophe. These observatories are ears pressed against the fabric of the universe, waiting for it to murmur. And the murmurs have come signals from black holes merging, neutron stars colliding, and perhaps future echoes of events we do not yet understand. The ingenuity embedded in these detectors shows the capacity of human inquiry to transcend limitation. We cannot travel to black holes, we cannot witness neutron star collisions firsthand, but we can build instruments capable of feeling their vibrations from across the cosmos. The universe does not need to be touched to be understood, it needs only to be listened to with extraordinary patience. What emerges from all this engineering is more than a machine, it is a new way of seeing, a new human sense. With it, we perceive the universe not only in light but in motion, not only in images but in ripples. LIGO and Virgo have become extraordinary listeners, tuned to frequencies that speak of creation, destruction, and evolution on unimaginable scales. And as these observatories continue to refine their ears, they will reveal even fainter signals, uncover new mysteries, and deepen our understanding of space-time itself. Their technology represents one of humanity's greatest achievements, the ability to shape matter and light into tools capable of hearing the universe's quietest songs. How these detectors work by bouncing lasers off mirrors, revealing infinitesimal distortions. The heart of these remarkable detectors lies in an idea so simple yet executed with such extraordinary precision that it becomes almost otherworldly. Send a beam of laser light down two long, perpendicular arms, bounce them off exquisitely suspended mirrors, and watch how they return. When a gravitational wave passes, even the tiniest stretching or squeezing of space alters the travel time of the light, creating a faint interference pattern. It sounds straightforward, almost like a classroom demonstration, but the scale, sensitivity, and sophistication transform it into a marvel that borders on the impossible. The lasers themselves are engineered to be unimaginably stable, producing beams so pure and consistent that any flicker, any deviation, would mask the faint whisper of spacetime's trembling. These beams travel down vacuum tubes stretching kilometers, isolated from dust, air, noise, and the chaotic movements of the world. Each mirror, polished to near perfection, hangs suspended by delicate systems designed to dampen vibration, because even the footstep of a person miles away, even the shifting of nearby soil, could drown out a cosmic signal arriving from billions of light-years away. It's a dance between fragility and resilience, precision and patience. Inside these observatories, silence becomes a fortress. The detectors don't merely observe light, They listen through it. The interference pattern formed when the lasers recombine is like a notebook in which space-time scribbles its faint messages. A passing gravitational wave might stretch one arm of the detector while compressing the other, causing the beams to return out of sync by distances far smaller than the width of a proton. Yet the system notices. It registers these impossibly tiny differences, translating them into a signal, a flutter, a hum, a momentary distortion that carries the story of two black holes spiraling together or neutron stars colliding in a fiery cosmic ballet. This technique relies on an ancient concept in physics known as interferometry, but elevated to an extreme that no one a century ago would have believed possible. In essence, the returning laser beams create a pattern of alternating bright and dark bands, interference fringes, that shift when the path lengths change. Under normal conditions, the fringes remain perfectly still. But when space-time itself ripples, even by an amount so small it feels meaningless, the pattern wavers. That tiny wobble is the gravitational wave announcing its arrival across the vastness of the universe. The mirrors function almost like ears, responding to the softest murmurs imaginable. Suspended in vacuum, cooled, controlled, and steadied, they float in delicate equilibrium. Any terrestrial influence, passing trucks, wind, thunder, even slight temperature differences, must be painstakingly filtered out so that only the authentic cosmic signal remains. It's a strange paradox. The universe's most violent events produce the weakest measurable disturbances, and humanity has created the quietest machines to hear them. The stability of the laser light ensures that when the beams split, travel, and return, any shift in phase can be measured with astonishing accuracy. The phase difference is like a heartbeat monitor for space-time, revealing whether the arms have been stretched or squeezed. Scientists must constantly fight sources of noise, thermal fluctuations, quantum fluctuations of the light itself, and even the jitter of the mirrors at atomic scales. The engineering solutions developed to minimize these effects form a silent triumph of modern physics. Quantum mechanics even becomes a collaborator in this delicate enterprise. The light inside the detector is so intense and so pure that its quantum noise, random fluctuations arising from the fundamental uncertainty of nature, become significant. To outwit these fluctuations, researchers inject squeezed light, a quantum-engineered state that reduces certain types of noise at the cost of increasing others. This careful trade-off allows them to push sensitivity beyond what classical physics alone would permit, reaching deeper into spacetime's faintest shivers. Every part of the detector must be stable beyond ordinary comprehension. Thermal expansion is the enemy. Even the tiniest change in temperature can cause structures to expand or contract, mimicking or masking gravitational waves. To counter this, components are crafted from materials that resist such changes, and environments are controlled to a degree that borders on obsessive. The detectors become temples of constancy, where the passing hours must leave no trace upon the instruments within. When the lasers finally reunite after their long journeys, the interference pattern is analyzed in real time by sensitive photodetectors. These devices must operate with such precision that they can distinguish between a single photon's timing and millions arriving in a coherent wave. The system records tiny changes in brightness, translating them into waveforms, patterns that scientists then compare to theoretical models to identify the astrophysical source, the mass, spin, and dance of the colliding objects. The beauty of the technique lies in its simplicity paired with breathtaking ambition. 2 arms, 2 lasers, 2 mirrors, yet what they measure requires sensitivity orders of magnitude beyond human intuition. The detectors don't see gravitational waves in any conventional sense. They infer them from changes in geometry. It is as if the laboratory itself becomes an instrument of measurement, allowing the structure of space to reveal its shifting shape. One extraordinary challenge arises from seismic noise. Earth itself is never still. It trembles constantly, from ocean waves crashing thousands of kilometers away, from tectonic processes, even from microseismic activity generated by human civilization. To overcome this, mirrors are isolated with multiple stages of suspension, pendulums upon pendulums, each layer filtering out more motion until the mirrors float with extraordinary stillness, ready to respond only to the universe's faintest nudges. The vacuum inside the detector arms is among the largest and purest ever created by humankind. Removing air is essential because air scatters light and creates turbulence, which would obscure the minute differences being measured. The vacuum tubes themselves stretch like silent highways across fields and plains, sealed and monitored continuously to ensure that nothing compromises their clarity. At the center of the detector, where the beams split and recombine, lies the beam splitter, a crystal plate that divides the light into two identical streams. This component must be crafted with microscopic uniformity, because any internal flaws or imperfections could introduce errors. It forms the crossroads where the story of each beam is written and then read upon its return. The mirrors are not mere reflective surfaces, they are masterpieces of optical engineering. Each one is coated with multi-layered dielectric materials that enhance reflectivity while minimizing absorption. Their surfaces are polished so perfectly that if they were scaled up to the size of a continent, no bump would exceed the height of a single grain of sand. And still, this is only just enough to catch the universe's trembling. The length of the arms amplifies the detector's sensitivity. The longer the light travels, the more pronounced the effect of a gravitational wave becomes. By extending the arms to lengths of kilometers, researchers have effectively created a magnifying glass for space-time distortions. With each reflection inside the arms, the light's journey is extended further, making the faintest changes perceptible. A gravitational wave passing through Earth alters the distances between objects not by pushing them, but by changing the geometry of space itself. In the detector, this means one arm grows slightly longer while the other shrinks, and a moment later they reverse. The mirrors follow this change passively, they are not pushed or pulled but instead move as spacetime dictates. The detector simply watches and measures. To ensure that environmental noise does not creep into the system unnoticed, auxiliary sensors surround the detector. Seismometers, microphones, magnetometers, and weather instruments constantly record the world around the observatory. Their data is cross-referenced with the main signal, allowing scientists to subtract or identify noise sources. Only when a signal is free from earthly interference does it earn the title of a true gravitational wave. Another elegance of the technique is that multiple detectors must confirm the signal. A gravitational wave washes across Earth, arriving at different observatories milliseconds apart. When LIGO's detectors in separate states detect the same pattern almost simultaneously, and Virgo in Europe echoes the same event with a slight time delay, the combined data pinpoints the wave's origin in the sky. The Earth itself becomes part of the measurement instrument. Inside the control rooms, scientists monitor readouts that appear almost serene, flat lines that mean nothing unusual is happening. But then, suddenly, a tiny blip emerges, a ripple that has traveled for billions of years, finally arriving to nudge mirrors by an imperceptible amount. Behind that small signal lies a cosmic drama, a collision, a collapse, a merging of massive objects that momentarily distorted spacetime itself. These detectors operate continuously, listening without pause, always waiting for the next whisper from the stars. They are indifferent to silence, patient in their vigilance. Every moment, they collect streams of data that must be analyzed, sifted, and compared against models. Most of the time, the data shows nothing but noise. But every once in a while, a real wave emerges, and the world of astrophysics changes. The data pipelines that process these signals are themselves masterpieces. Sophisticated algorithms sift through torrents of data, identifying potential candidates. Machine learning and human intuition work hand in hand, examining patterns and correlating them across detectors. Detecting a gravitational wave is not simply a matter of recording movement, it is an orchestration of mathematics, engineering, and cosmic storytelling. Even the Earth's gravitational pull must be accounted for. Tidal forces from the Moon and Sun cause subtle stretching of Earth's crust, which can mimic the effects of gravitational waves if not properly measured. The detectors compensate automatically, adjusting their baselines to preserve accuracy. The heavens influence the planet in more ways than one, and the detectors must stay ahead of these effects. When a confirmed gravitational wave event is finally identified, the data is preserved with reverence. It is not just a measurement, it is a message, a direct imprint of cosmic violence. The waveform becomes a fingerprint of celestial objects, revealing their mass, their final moments, the energy released, and the space-time choreography they performed before merging. Each detection is a story written in the language of gravity. And in all of this, the detectors themselves remain silent witnesses. They don't speak, they don't shine with glory, they simply persist, tirelessly bouncing lasers between mirrors, waiting for the next minuscule change in distance that signals something unimaginable has happened far beyond our sight. They transform the invisible into knowledge, the distant into the present, and the faint into the astonishing. What's most remarkable is that these instruments have opened a new way of observing the universe, one based not on light, but on motion woven into the fabric of space. By bouncing lasers off mirrors with precision beyond imagination, they have made the intangible measurable. And with each tiny distortion they reveal, they invite us to hear the universe in a way humanity never could before. If you'd like part 6, just tell me the line to begin with. The awe-inspiring moment the first gravitational wave was detected, confirming a cosmic whisper. The awe-inspiring moment the first gravitational wave was detected, confirming a cosmic whisper, was not a dramatic explosion of alarms or lights but a quiet pattern emerging on a screen, an elegant, rising chirp that seemed almost too perfect to be real. For decades, scientists had pursued this dream, building colossal instruments and refining theories, yet when the signal finally appeared, it did so with a gentleness that belied the violence of its cosmic origin. Two black holes, each tens of times the mass of our Sun, spiraled together and collided over 1 billion years ago, sending ripples across the fabric of space-time that finally arrived at Earth as a fleeting tremble. In that understated moment, a century-old prediction took its first breath of reality, bridging Einstein's imagination with humanity's instruments. In the quiet control room of the LIGO observatory, researchers watched as the signal unfolded in real time, a pattern so clean and recognizable that it seemed like a cosmic melody. It was not noise, not a glitch, not a quirk of machinery, it was something profoundly intentional, shaped by the final milliseconds of a cataclysmic merger. When they compared it to their theoretical templates, the match was uncanny. Every curve of the waveform whispered the same truth: space-time had spoken at last. This was not just detection, it was confirmation, validation, and revelation all at once. The universe had finally granted a new sense to humanity, a way to hear gravity itself. To ensure they weren't deceived by terrestrial interference, the team checked data from both detectors, the one in Louisiana and the one in Washington. The signal had appeared in both, separated by a fraction of a second, exactly consistent with how a gravitational wave would sweep across Earth. This tiny delay became the signature of authenticity, the universe's own timestamp. The correlation left no room for doubt. Even the skeptics, those cautious souls who had guarded against premature celebration, found themselves stunned into silence. And in that silence, a new era of astronomy opened. The signal, later named GW 150914, held within it an entire cosmic narrative. By analyzing its shape, frequency, and amplitude, scientists could reconstruct the last moments of the two black holes before they merged. They spun around each other faster and faster, ultimately reaching velocities close to the speed of light before colliding into a single, larger black hole. The energy released in that instant was so immense that, for a fraction of a second, the power output exceeded that of every star in the observable universe combined. Yet the earth-shaking force of this event arrived here as a disturbance smaller than the width of a proton, a whisper crossing a billion-year gulf. The scientific community responded with disbelief, then astonishment, and finally elation. Theories long treated as abstract elegance were now living descriptions of the universe. For decades, people had wondered whether gravitational waves actually existed or whether they were just mathematical curiosities. Now, there was no question. Einstein had been right not just in principle, but in measurable, undeniable detail. It felt as if the universe itself had nodded in agreement with the equations etched on old chalkboards. But beyond the physics, there was a human element, thousands of people who had devoted their careers to this pursuit. Engineers, theorists, data analysts, technicians, and students had labored for years, sometimes decades, chasing a signal that many feared might never come. When the discovery was announced, some cried, some laughed, some simply sat still, overwhelmed by the enormity of it. They had reached into the deep night and found proof that gravity could sing. Their persistence had turned suspicion into certainty and dreams into data. The announcement in February 2016 became a moment etched into scientific history. News outlets buzzed, headlines captured global attention, and the world paused to consider what it meant. For the first time, humanity had directly detected a phenomenon Einstein predicted in 1916, a full century earlier. The timing felt poetic, almost scripted by the universe itself. 100 years of theory culminating in one clean signal, one cosmic note that resonated across the world and across time. Though the signal lasted merely fractions of a second, its implications stretched infinitely wider. It marked the birth of gravitational wave astronomy, a field that promised to reveal hidden stories of the cosmos. Black holes, once invisible except through their influence on nearby stars, could now be studied through their own violent interactions. Mergers, explosions, and dense stellar remnants became accessible in ways that telescopes alone could never achieve. The detection expanded not just knowledge, but possibility. The triumph also validated the enormous engineering effort behind LIGO. These were not just detectors but monumental achievements in human ingenuity. To measure distortions so tiny required technology operating at the limits of the possible. The first detection proved that such ambition had not been misplaced. The entire apparatus, vacuum chambers, mirrors, lasers, and suspension systems had performed like an instrument finely tuned by both science and hope. One of the most profound aspects of the moment was how quiet it was. There was no dramatic surge in the control room, no cinematic rising soundtrack, just a subtle shift in data, a small blip that spoke volumes. That simplicity made it even more beautiful. The first gravitational wave arrived without fanfare, a ghostly ripple that could have gone unnoticed without decades of preparation. It reminded everyone that the universe's greatest messages often whisper rather than shout. As researchers revisited the data again and again, they found new layers of meaning. The waveform revealed the mass of the black holes, their spins, their distance, and the energy they emitted. It even allowed scientists to test general relativity in extreme conditions, conditions that would be impossible to recreate in laboratories. Every aspect of the signal aligned with Einstein's predictions. It was as if the merger had been waiting billions of years simply to prove him right. The scientific paper announcing the discovery became one of the most cited works of modern physics. Its figures and graphs circulated worldwide, from classrooms to research institutes. Students studied it with awe, recognizing that they were witnessing the start of something monumental. For many young scientists, it ignited careers, setting them on paths toward gravitational wave research. Inspiration rippled outward just as the wave itself had done. The broader scientific community quickly embraced the implications. Gravitational waves provided a new tool for understanding the early universe, the nature of black holes, and the behavior of matter under unimaginable pressures. Where telescopes reached their limits, blocked by dust, distance, or the absence of light, gravitational waves offered a way through. They traveled unimpeded, carrying untarnished information from the most extreme corners of existence. Amidst the celebrations, there was also humility. The signal reminded everyone how small Earth is compared to the cosmic events unfolding around it. Two black holes had collided long before humans existed, and only now had the faint echo reached us. It was a humbling reminder that the universe moves on scales of time and power far beyond human perception. Yet it was also empowering, because, despite our smallness, we had built instruments capable of detecting the universe's faintest tremors. In the weeks that followed, scientists went back through archived data. They wondered, had they missed earlier signals? Were gravitational waves hiding in the noise before the detectors were fully upgraded? Indeed, they later found additional events, each one reinforcing the reality of this new observational medium. But nothing compared to the first, the one that broke the silence. GW 150914 became more than a label, it became a milestone. It marked the first time humanity heard the cosmos. The waveform itself became iconic, a rising frequency often described as a chirp, stretching upward as the black holes spiraled together. This chirp was played in classrooms, documentaries, and science festivals. It was not just data, it was sound, a literal audio representation of space-time deforming. Teachers used the detection to inspire students, explaining how the universe communicates through gravity. Public lectures drew crowds eager to understand how something so faint could be detected so precisely. The discovery transcended scientific boundaries. It became a cultural event, touching people who had never before considered the physics of space-time. The moment also changed how astronomers collaborated. Traditional observational astronomy and gravitational wave astronomy began working hand in hand. When later detections included light, such as merging neutron stars, teams around the world coordinated telescopes, detectors, and satellites. An entirely new era of multi-messenger astronomy had begun. But it all traced back to that first signal, that first confirmation that gravitational waves could be caught. Even today, scientists recall the moment with wonder. They speak of the stillness in the room, the disbelief on their faces, the thrill that ran through them as they realized what had occurred. It was a moment that blended the past and the future, Einstein's distant vision meeting modern technology. The room held not just researchers but generations of intellectual effort. In the days surrounding the announcement, interviews and documentaries captured the emotional side of the discovery. Researchers described sleepless nights, endless data checks, and the weight of responsibility. When the final confirmations were complete, relief washed through the collaboration. They had not just discovered gravitational waves, they had changed humanity's relationship with the cosmos. The awe of the moment lingers because it represents a rare intersection of human dedication and cosmic timing. The wave had traveled for more than 1 billion years, crossing empty voids with no guarantee of ever being perceived. It might have passed Earth unnoticed if not for the detector's readiness. The coincidence of our technological era aligning with the wave's arrival felt almost poetic. And yet, the discovery was not luck alone. It was the culmination of effort built across nations, institutions, and decades. It represented the triumph of cooperation, vision, and persistence. It showed that even the most difficult scientific dreams can be realized when humanity reaches past its limitations and builds something extraordinary. The first detection also helped refine the detectors themselves. Scientists analyzed how the signal behaved, how noise fluctuated, and how the instruments responded. This led to improvements that later enhanced sensitivity, enabling even more detections. The wave served not just as a discovery but as a teacher, revealing ways to sharpen our cosmic hearing. With each passing year, the significance of that moment grows. It stands as a threshold event, the bridge between a world where gravitational waves were theory and a world where they are a routine part of astronomy. The universe suddenly became more accessible, more vibrant, and more dynamic. That first whisper opened countless doors. Even now, when scientists replay the wave's chirp, it evokes a sense of reverence. It is the sound of two black holes completing their ancient dance. It is the sound of space-time shuddering. It is the sound of a century-old prediction finally standing before the world. And in that sound lies the reminder that the universe is always speaking, always moving, always shifting. The first detection was a moment when humanity caught the universe in the act of creating something extraordinary. It transformed silence into knowledge, whispers into understanding, and ripples into revelation. In that tiny tremble of space-time, humanity gained a new sense, a new window, and a new way to listen to the cosmos that surrounds us. The astonishing sources of these ripples, colliding black holes, merging neutron stars, and supernovae. These cataclysmic engines of the cosmos create disturbances so immense that space-time itself shivers with their passing waves, trembling like the surface of a pond after a stone has been cast into it. When we imagine black holes spiraling inward, each orbit faster than the last, each moment charged with unimaginable tension, we begin to glimpse the raw power behind these cosmic murmurs. The fabric of reality cannot help but quiver beneath such titanic dances, sending out signals that travel billions of years before brushing gently against the detectors we build on Earth. These events begin as silent ballets in deep space, too far and too immense for human senses to register, yet their influence is vast enough to stretch and compress the very coordinates of existence. Picture two black holes drawing close after eons of circling, their mass warping the surrounding space-time so intensely that even light must bend to accommodate their presence. As they spiral together, the frequency of their gravitational whisper rises, forming a crescendo that ends not in light or flame, but in a sudden merging into a single, unified shadow. And yet, though the union is silent to ordinary ears, the universe records it with a final tremor that rings across the galaxy like a ghostly bell. Merging neutron stars, too, contribute to this symphony, though their song is different in texture and tone. These are the compressed remnants of once glorious stars, reduced to spheres only kilometers wide yet heavier than the Sun, containing matter so dense that a teaspoon of it outweighs mountains. When two such remnants fall toward each other, magnetism, gravity, and nuclear pressure interact in ways almost incomprehensible. Their collisions release both light and gravitational waves, sending bursts of gamma radiation blazing outward and crafting heavy elements like gold and platinum in the turbulent aftermath, scattering them like cosmic confetti. Supernovae, on the other hand, unleash chaos on a scale grand enough to reshape entire star systems. When a massive star reaches the end of its life, its core collapses with a force that defies adequate description. The outer layers rebound outward in a cosmic explosion that can outshine galaxies for a brief moment. In the heart of this collapse, the sudden shift in mass distribution triggers gravitational waves that radiate outward, though faint compared to those generated by compact object mergers. Yet even faint waves from such an event carry stories of collapsing iron cores, rebounding shockwaves, and the birth of neutron stars or black holes from stellar ashes. The universe contains a ceaseless rhythm, and it is in these violent celestial moments that its deepest beats reveal themselves. Every collision, each implosion, every merger is like the heartbeat of an organism too immense for us to fully imagine, and we, with our delicate detectors, stand at the edge of understanding, listening to the faint echoes of its pulse. As these waves pass through the Earth, They stretch and squeeze our planet by distances far smaller than a proton's width, yet they carry within them clues about distances, masses, spins, and the dances of bodies that no eye can ever witness. Even though we cannot see these events directly, their gravitational footprints carve patterns into the instruments we build. It's astonishing to realize that something as abstract as the curvature of space-time can leave marks on our machinery, that the universe's most secret catastrophes imprint themselves as oscillations on lasers and mirrors. The collisions of black holes, silent in every conventional sense, are loud in their gravitational voice, shouting across cosmic expanses until, at last, the faint remnants of that shout brush against our world. Black hole mergers are particularly dramatic, for they represent the final moments of a relationship that may have started billions of years earlier. Imagine two stars orbiting peacefully, each burning brightly until one collapses into a black hole, and then perhaps the other follows. Over countless ages, their orbits decay, drawing them ever closer. In their final seconds, they whirl around each other at nearly the speed of light before coalescing, creating ripples so intense that space-time itself heaves in response. Those ripples travel outward forever, carrying with them the memory of their violent birth. Neutron-star collisions, though different in structure, carry their own brand of celestial magnificence. These stars are not just dense, they are exotic, containing matter in states that cannot be replicated on Earth, matter squeezed so tightly that atoms cannot remain intact. When two such bodies collide, tides of nuclear material slosh across their surfaces, immense magnetic fields twist and snap, and radiation bursts forth in beams that could sterilize planets. The gravitational waves they emit offer scientists unique insight into the physics of dense matter and the origins of heavy elements essential to life and civilization. The complexity of these events can lull the mind into imagining chaos without order, but the truth is that their motions follow the rules of relativity with exquisite precision. Einstein's equations predict the spirals, the inspirals, the mergers, and the ringdowns with uncanny accuracy. The waves carry not just energy but encoded information, subtle signatures that reveal how the final object settles into equilibrium after its furious birth. By listening closely enough, scientists can determine whether the final remnant is a black hole, a hypermassive neutron star, or something in between. Supernovae, although not as strong a source of gravitational waves, fill another essential role in shaping cosmic evolution. They seed the universe with elements heavier than helium, elements necessary for planets, life, and the structures from which detectors like LIGO are built. Their gravitational waves tell of collapsing stellar cores, the swift formation of neutron stars, and the rebounding shock fronts that sweep outward. Though weaker, these waves, when detected, would allow us to peer directly into the heart of a dying star, witnessing processes hidden behind layers of incandescent plasma and light. Each of these cosmic events, collisions, mergers, collapses, represents a transformation, the universe reshaping itself in flashes of energy and waves of distortion. These transformations echo across the ages, like distant memories carried on a breeze. When they reach Earth, we capture them not with our senses but with instruments that have been engineered to listen to the very heartbeat of the cosmos. These detectors translate the silent tremors into patterns, curves, and data streams, allowing us to read the narratives written in spacetime itself. The sheer scale of these processes is humbling. Imagine two black holes 30 times the mass of the Sun spiraling together. The energy emitted as gravitational waves in their final moment exceeds the light emitted by all stars in the observable universe combined, even though the event itself emits no light at all. It is a paradoxical blend of intensity and invisibility, power and mystery. The universe writes its most dramatic stories in forms that evade ordinary perception, but still it offers clues to those who know how to listen. Sometimes, when contemplating these violent cosmic events, one might imagine them as storms in an ocean deeper and broader than any earthly sea. The black holes are whirlpools, neutron stars are compressed islands of unimaginable weight, and supernovae are colossal waves crashing upward from the abyss. Gravitational waves become the ripples that extend outward from each tempest, carrying with them the memory of the storm's shape, even long after the storm itself has died. The remarkable thing is that these waves never fade completely. They stretch across billions of light-years, across unimaginable epochs, through regions where galaxies form and others dissolve. They move untouched, whispering their secrets to any who can detect their presence. They are like letters sent across cosmic distances, sealed in envelopes of warped geometry, awaiting deciphering by creatures who evolved on a small blue planet far from the event itself. Merging neutron stars, for instance, may produce electromagnetic afterglows that accompany their gravitational signals. These afterglows allow astronomers to triangulate the location of the collision and study its remains. By combining light and waves, we build a deeper, more intricate understanding of the universe. The gravitational waves mark the rhythm of the event, while the electromagnetic signals paint the color and texture of the aftermath. Together, they form a fuller portrait of the cosmic spectacle. Black hole collisions, in contrast, leave no luminous traces. They vanish silently into darkness, the final black hole sealing the event within its horizon. Only gravitational waves escape. These events, therefore, teach us to listen more creatively, to seek understanding in vibrations rather than illumination. They challenge the assumption that knowledge must always arrive through light, reminding us that the universe speaks in many languages, some of them subtle, some of them ancient and all-encompassing. Supernova gravitational waves, though rarely observed, offer the possibility of reaching behind the veil of light produced in these catastrophic explosions. They contain information about the asymmetry of the collapse. A perfectly spherical implosion produces almost no gravitational waves, only lopsidedness creates the disturbance necessary to radiate spacetime ripples. Thus, the waves can reveal imperfections hidden within the heart of the star, imperfections that shape the entire outcome of the explosion. Each source of gravitational waves also contributes to a cosmic map. Over time, as detectors improve, scientists hope to observe not just isolated events but a background hum of countless weak signals, the combined whispers of millions of ancient mergers. This background would be a kind of cosmic fossil record, preserving traces of the earliest black hole formations, the first neutron stars, and the remnants of the universe's tumultuous youth. Listening to this background is like hearing the ocean's roar made of countless overlapping waves. The violent union of compact objects is fascinating not only for what it reveals but for what it challenges. These mergers often push physical theories to their edge, confronting scientists with conditions impossible to replicate in laboratories. The density, gravity, and curvature at play during these moments are so extreme that they test the boundaries of nuclear physics, general relativity, and quantum mechanics all at once. Gravitational waves, therefore, become tools for exploring physics beyond what can be achieved on Earth. The fact that we can detect these faint waves at all is a testament to human ingenuity. The sources may be violent beyond comprehension, but by the time their ripples reach us, they are so faint that only the most delicate measurements can detect them. These signals carry stories of creation and destruction, of spirals and collisions, of deaths and births, and of the ever-changing landscape of the cosmos. To catch even one such wave is to receive a message written across the vastness of interstellar space. When neutron stars collide, they create not only gravitational waves but also kilonovae, brilliant, short-lived explosions rich in heavy elements. These luminous flares reveal how gold, platinum, and other rare elements form, connecting the grandeur of cosmic violence to the everyday materials we wear, use, and treasure. Every ring on a finger, every piece of circuitry in a device, may contain atoms forged in the fire of a long-ago merger. Thus, gravitational waves connect us to the history of matter itself. These collisions also allow astronomers to measure cosmic distances in new ways. Gravitational wave signals can act as standard sirens, announcing the distance to their source with great precision. When combined with measurements of redshift from accompanying electromagnetic signals, they offer a new method to study the expansion of the universe. In this sense, merging neutron stars serve as beacons, illuminating both their own nature and the broader cosmic environment in which they occur. Black hole collisions deepen our understanding of space-time geometry. When two black holes merge, the resulting object undergoes oscillations known as ringdown, settling into a stable form predicted by general relativity. The frequencies of these oscillations act like the tones of a bell, revealing the properties of the final black hole. These tones can confirm or challenge theoretical predictions, making each detection an opportunity to test the very foundations of modern physics with exquisite precision. Supernova gravitational waves may one day help resolve mysteries surrounding stellar collapse mechanisms. The exact processes that determine whether a star becomes a neutron star or collapses into a black hole involve complex interplay between neutrinos, shock waves, and nuclear forces. Gravitational waves can provide clues unavailable through any other means, cutting through the blinding light and turbulent plasma to reveal the core dynamics with unmatched clarity. The sources of gravitational waves also extend beyond the objects we can easily imagine. Some theories predict the existence of exotic sources such as cosmic strings, hypothetical defects in spacetime left over from the early universe. If these strings exist and oscillate or break, they would produce gravitational waves unlike any generated by astrophysical bodies. Detecting such waves would open an entirely new chapter of cosmology, connecting observational astronomy to high-energy physics and the universe's earliest moments. Even in the absence of exotic objects, gravitational waves offer a window into regions of the universe otherwise inaccessible. Black holes created in dense stellar clusters, mergers happening near galactic centers, or collisions occurring in dust-obscured regions can all be observed through their gravitational signals. In this way, gravitational waves serve as a universal messenger, unconstrained by light and unimpeded by cosmic obstacles. As detectors continue to improve, we will begin to observe mergers at greater distances, reaching deeper into cosmic history. With each new detection, the universe becomes more transparent, revealing the processes that shaped galaxies and star clusters long before our Sun existed. We will see not only the recent ripples of modern collisions but also ancient echoes from the universe's more chaotic and energetic past. In a sense, gravitational wave astronomy transforms the cosmos from a silent panorama into a dynamic, resonant symphony. Instead of simply watching, we are now listening to the vibrations left behind by the most extraordinary transformations in the universe. Black hole collisions become percussion, neutron star mergers become melodic pulses, and supernovae add sharp, transient bursts of intensity. Through these waves, the universe speaks in a language that predates stars, planets, and life itself. These ripples remind us how small we are and yet how connected we remain to the grand processes that shape everything. Even the faintest gravitational wave alters Earth ever so slightly, stretching and compressing the ground beneath our feet. These distortions are imperceptible to human senses, but still, we are physically moved by cosmic events billions of years old. It is a humbling and beautiful truth that the universe leaves fingerprints on us even from its farthest, darkest corners. And so these astonishing sources, colliding black holes, merging neutron stars, and explosive supernovae, form the backbone of a new, deeper way of understanding our reality. They are the architects of the universe's structure, the sculptors of galaxies, the creators of heavy elements, and the originators of waves that traverse all of space-time. As we continue to listen, we may uncover symphonies still unknown, harmonies still unheard, and cosmic stories still waiting patiently to be found.